All right, we are going to take a look at a new parent function. This doesn't look like a new one. This looks like one that we already have, but the truth is we already know a lot about the new function that we're looking at. One thing that we never did with this exponential growth function, this isn't everything you had on the notes there, but I'm going to start from it here. We never answered the question, how do we reverse this process? What is the opposite of the exponential growth function, or what we would call the inverse of the exponential growth function? Arrow going right here, it tells us these, when we're doing the inverse, these are the starting points, these are the ending points. So we know that starting at 0 should take us to a negative infinity. Starting at 1 over b should take us to negative 1. So these points that were outputs for the exponential become the inputs for the inverse of the exponential. Okay, so I'm going to start down here by saying I'm going to make the arrow diagram. Okay, and I'm going to put the points on there. Now, there is no negative infinity here. What was the domain, what was the range of the exponential function now becomes the domain. It's all about switching inputs and outputs, and domain's about input and range is about output. So if these were the outputs before, they now become the inputs, and that looks like they're probably in numerical order there. So I'll go with the 0. I'm going to put in a 1 over b, a 1, a b, and an infinity. Okay? And I'm going to scoot those up so you can actually see those. Okay? And then the outputs that go with them, the 0 now goes to a negative infinity. The 1 over b goes to negative 1. The 1 goes to 0. The b goes to 1. And the infinity goes to infinity. So we recognize this bottom part here of infinity going to infinity there. We recognize that type of in behavior. Okay. It's going to look a little bit different on this one than we're accustomed to. If we plot some of these points, this now says that as we're getting close to 0, well, we'll come back to that one. Let's put some other points out here. So let's put 1 out here. Let's put b, which we know would mean 1 over b is in here somewhere. And output of negative 1, output of negative infinity obviously is way down here. Output of positive infinity is up there. The 1 over b, when we input a 1 over b, we get a negative 1 as an output, so that gives us that point. When we input a 1, we get an output of 0, so that's an x-intercept. That was the point that was a y-intercept. We said inverses are about switching the roles of the x and the y, so what was at 0, 1 as a y-intercept is now at 1, 0 as an x-intercept. And at b, we are at 1. Okay? This behavior over here, this in behavior that we described as a horizontal asymptote that was getting closer and closer to the x-axis the farther we went out the x-axis. Well, if this is about switching things, then that would be the farther we go down the negative y-axis, the closer this gets to the negative y-axis. And so based on where this is, this must look something like this. It comes up there very close to the axis, then starts to bend away, okay, and goes off in this direction. Okay. So, sorry about the announcements in the background there. We can kind of see the comparison here where this goes, this looks almost flat going out there towards the positive x-axis, the way that this looked almost parallel to the positive y-axis. It doesn't get parallel though, it keeps climbing because we know as we go toward infinity, it goes toward infinity. So our end behavior over here is that as x approaches infinity, f of x also approaches infinity. This is a weird thing though. Before up here we called this a horizontal asymptote because it flattened off horizontally. This goes vertical. This is actually called a vertical asymptote. So my vertical asymptote is the behavior that's going on there, and I see it here in my arrow diagram. There is literally nothing happening over here. There's no inputs that work for this, so this is our first thing that we had that had a really restricted domain. Our domain here says that the x values have to be bigger than 0. We had said the range on the exponential function had to be y values bigger than 0. So we switched the x and the y. But we can get all real numbers here for the range of this function. So we know everything about it except for the name of it. And so we need to come up with the name of this. Many years ago, the first guy who gets to name it gets to have his name for it go down in history. This is called the logarithm. And this works as the inverse for whether it's exponential growth or exponential decay, does not really matter. Okay? So for the logarithm, it looks, the way that he chose to write it was log, and then he would name the type of logarithm depending on what the base of the exponential had been. So the base of our exponential is b. So this is log base b of x, and we can cover the growth and the decay by saying that the b is either between 0 and 1, or the b is bigger than 1. B can't be 1 and b can't be negative. Same restrictions that were on our exponential growth and exponential decay. Okay. So this becomes a log base b empty set of parentheses, and this is what we call our logarithm parent function. This is the inverse operation to exponential growth. So on my exponential growth here, I could put up here that if I want to go the opposite of b to the power, I need log base b of. Okay, this is an unfamiliar thing. Okay, to us, this is maybe your first introduction to the logarithm function. Okay, but it's something obviously that we would want to have. If we don't have this, then solving exponential equations becomes a very painful guessing and checking process. And so this is what we want you to know about this to this point, and we will move on from here as we wrap this up, and we'll learn more about the logarithm and its properties the same way that exponential functions had properties.